So, greetings. So in this video we will learn a few things about the language Prolog, which is a logic programming language, logic programs. First, I will give you an example of a logic program. It will consist of three, well, you can call them statements if you wish. In logic programs, we usually prefer the term clauses for those statements. So, and I will just sketch them up and then tell you about the meaning of these things. Usually, such a clause looks like an implication, and that's because it's an implication. So, it says that, for example, our first clause can say that even x implies odd successor of x. Okay, and this x is the same. So the second one says that odd x implies even successor of x. And then the last one says that, say, 0 is even. Okay, so this is a very small program. It's a valid program in Prolog, apart from the syntax itself, because it's not ASCII, but yeah, so there is an equivalent Prolog program consisting of about almost the same amount of characters. So, and usually when a programmer writes such a program, then in their mind these three statements have the following meaning. If x is an even number, then the successor of x, so it's x plus 1, is an odd number. Yeah, that's true. Okay. And the second one says that if x is an odd number, then the successor of x, so x plus 1, is an even number, which is also true. And the third one says that 0 is an even number. So usually, and that's also true. So that's usually the meaning, the semantics of these clauses or statements. So I will stick to clauses when a programmer types this. But for the computer, these are just strings. So these are just well-structured strings. But for a Prolog interpreter, the x has no meaning where the values can come from. So x can be a number or a snowman or a week of the day, whatever. So what the Prolog program knows is just that this x denotes some sort of an object. It's okay if the programmer has, say, natural numbers in their mind during programming, so you can think that the objects will be natural numbers, but the computer, the interpreter, won't necessarily assume that the objects will be natural numbers. And of course these functions or predicates, odd, even, and the s letter, and even the 0 as something denoting constant, carries absolutely no meaning for the Prolog interpreter. So an important thing to learn is how to teach the Prolog engine which objects we are talking in our programs. So basically, what are these? So the x in such a program is a variable. If you are familiar with first order logic, I hope you are, so then these are first order variables. So variables takes an object as value. from some set of objects, which here is called a universe, from some universe. Okay. And then we have the odd and the even, which sounds like, well, adjectives. It's either true or not. So the odd and the even, well, I won't say function symbols because these are things which are called predicates in first order logic. So it's predicates. And such a predicate or predicate symbols, so at this point they are only names. They will denote something which takes an object and outputs a truth value, either true or false. So take some objects. Well, in this example, the even is or takes only one object and the odd takes only one object. But for example, if I would use the smaller than or equal to predicate, that takes two objects and returns true if the first object is smaller than or equal to the other one. So predicates can have arity, so that's how it's called, the number of possible parameters the predicate can take. So the arity can be 1, like in this example. It can be 2, like the example of equals or smaller than or equal to. It can be 3, 4, whatever you wish. And it can be even 0, in which case you will just have a Boolean value, so it's either true or false, independent only of the input, because there is no input. So the predicate symbols, which will take some, in some world, these will take some objects and output to a truth value. Now, in the beginning, there will be only two truth values, the true and the false. Okay, true will be denoted by 1 and false will be denoted by 0. Now this S here is something else because, as we've discussed, even takes an object, which means that S should output an object and not a truth value. So this S here is a function symbol. Function symbol. And function symbols will denote functions, which will take objects, some objects, as input and output an object as output. So it's basically an object to object mapping. It denotes some object to object mapping. So for example, the successor is a function because it takes a natural number and outputs a natural number. Addition is a function because it takes two numbers, objects, and then it outputs a number also. Multiplication is also a function. So the difference between functions and predicates is lies in the output type. So the predicate will output a Boolean value and a function outputs some object value coming from some fixed universe of symbols. And it also has an arity. In this case, the S is a unary function because it takes one object. You can use binary function symbols, and the 0 is also a function symbol taking 0 arguments. So the 0 is just a name of a function. If you want to be more precise, then you just you can write the 0 like this. So the 0 is a function which takes no arguments, and if you just want to well compute the value produced by this function 0, then you can call the function like this. But I usually get rid of the empty parentheses because it's quite Well, so it's not that not that visually pleasing to have these empty brackets after the constant terms. And this here is just a logical implication. Okay, and in logic programs, implications will have one single statement, an atomic formula on the right hand side, and the conjunction, so this and this and this and this, on the left hand side. On the left hand side there can be more things, more atomic statements, and they have to be under the conjunction operator, so and this and that and that and also that implies this, and this is how a close of a logic program looks like. No negation involved yet, but in a normal product program there won't be any negations. So let's just be a bit more formal. So for the syntax, variables say it's x1, x2, x3 and so on. Of course, in some real life scenario we are using also y, z and so on and so on, but just to be well defined, let's just use these variables x1, x2, x3 and so on. And then we have function symbols. Function symbols, they are usually denoted by f, f1, f2, f3 and so on, f1, f2 and so on, each having some arity, the number of objects you can substitute formally into a function symbol. So each having an so-called arity, which is just a natural number being at least 0. So I will use green for examples. So for example, the plus function symbol is a binary operation, and this is how we usually denote this. The function's name, slash, and the number of operators it can take. So it just says that the plus is a binary operator, and this is a function symbol. And for example, you will have the multiplication operator, which is also binary, and you can have the minus operator as a unary thing. So this is the unary minus, for example, and you can just say that the successor function is also unary, for example. And for constants, for example, 0 was a constant in the previous example, you can use the arity of 0, which means that 0 is the name of the function which takes 0 inputs. Yeah, okay. And from these two things, from variables and function symbols, we can build terms. This is how they are called. From these we build terms. A term is just something which eventually will denote an object. So in our previous slide, here x was a term because it's a variable. X, okay. S of x is also a term because it's built from a function symbol and a variable, and the number of possible arguments is taken into account. And this 0 here is also a term because if you just write it here, it's clear that you are just only using function symbols and variables to build up this term, and of course parentheses and commas if you are just writing these terms in. Okay, So eventually these terms these terms will denote objects from some specific universe of objects, but it's not the part of the syntax. You only give the syntax to Prolog, and you won't give semantics to Prolog. So actually the course deals with the question, how does the Prolog engine defines semantics, an underlying universe of objects, which universe it deals with, and so on and so on, automatically, because the programmers won't tell the engine explicitly which universe to use, what are the meaning of the function symbols. So in this course we will learn how the program assigns semantics to a logic program. Okay, so we will terms, and an important concept is a ground term. A ground term, it's a term with no variables. Term with no variables. So for example, if our alphabet, our signature is this guy there, then for example 0 is a ground term because it's a term and it has no variables. But since we have the 0, we can use the successor of 0, for example. That's also a ground term because it's just built out of function symbols. So basically you can start from a constant and apply some function symbols of arity larger than 0 on your values. So you can get, say, 0 plus s of 0, this is also a ground term, and for example say s of 0 times s of 0, like this, and so on, if you don't use variables. So these are ground terms. Okay, and not necessarily so if you are building terms which are not necessarily ground terms, then you can build, say, s of x, because then you can just use the variables. If you wish, you can index these, so s of x1 or x1 plus the successor of x2, that's also fine, and like 0 times successor of x, that's also fine. So that these three guys are terms as well, but they are not ground terms. These guys here are terms and they are ground terms. Okay, so that's a term. Now from objects we can build up, well, statements regarding objects using these predicate functions. So it's still the syntax. So there are also predicate symbols. Predicate symbols, they are usually denoted by P1, P2, and so on, Q, or names like even, odd, and so on, each also having an arity. Each having an arity. It's also an arity at least 0, so 0, 1, 2, or something like that. So for example, a predicate symbol can be the equality sign, which is always a binary stuff. Or you can use the smaller than or equal to, and it's also binary. Now, for example, this even sounds like an adjective and it's like a unary predicate, and in the context of natural numbers this guy usually denotes the predicate which is true if your number is even and false if your number is not even but odd. So for example, odd is also one particular predicate symbol which you can use, and so on. So you can just invent or rename predicates if you wish, but of course these signs are usually denoting something which is either true or false. Those functions which we've seen on the previous slide, the multiplication and so on, is not evaluating into true or false, but those are evaluating into object values. So of course that's why we are just in our notations we are just using a different section of the alphabet to denote function symbols and predicate symbols, because they will have a quite different meaning. Now a formula, an atomic formula so an atomic formula is just P of T1, T2 and so on, Tn, where P is an n-ary predicate symbol, and these T's are terms. Okay, so basically we have to take a predicate symbol and substitute the appropriate number of terms into this symbol. So for example, like x equals s of x. That's an atomic formula. You can write it like this, equals x s of x, but usually predicate symbols, when they are binary, are just written in fixed notation. So it's the same. And usually human beings try to prefer the previous one, so the first one, the x equals sx notation. And of course the even of x is also a valid predicate. It's a unary predicate, okay, even if our alphabet contains this predicate even and it's unary and x is a variable, then it's fine, because then x is a term, so we are just substituting one term into a predicate symbol. So this is how we create atomic formulae. And the clause is just says that, well, I shouldn't use p for that, so it just says okay, so I should just f1 and f2 and blah 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 and n implies g. Okay, so this is how a logic program's clause looks like, and the f's and g's are atomic formulae. N can be 0 as well, and the empty conjunction always evaluates the true. So just to have some intuition behind this is that the more things you just put into a conjunction, it's less likely to have a true value, right? So it's the more things you are just ending, you will have a smaller and smaller chance to have a true value, because the conjunction is one only if all the components are evaluated into one, which is the reason why the empty conjunction will be evaluated to true. So basically that's for the syntax for the logic program, because we've already seen these. This is an implication, okay, this is an atomic formula here, this is also an atomic formula there, this is also an atomic formula there, this is also an atomic formula there, atomic formula there, an empty left-hand side, and left-hand sides of a single argument. So it's fine. So then we are just say that a logic program is just simply a set of clauses. So And this is important, that the clauses, the order of the clauses is not important in a theoretical logic program. I mean, probably the order of the clauses will be important actually, because the prolog is just carrying out some operational semantics. But what the prolog tries to achieve is to compute the notational semantics using these operational semantics. So in theory, for the denotational semantics, the order of the clauses should not matter, right? So that's why it's not a sequence of clauses, but it's just a set of clauses. Okay, so a program is a set of clauses. Good. And we should just define the semantics of a logic program, and I will do that. So the semantic is just the meaning of a program, possible meaning of a program at this point. So for the semantics, a model of a logic program let's call this program P. It's a capital standard P. I will use P's for a number of different types of objects, so please try to follow the capitalization and the font of the P's I'm trying to use. So P for program. So the semantics as a model of a logic program P, which just a set of objects, say A of objects, and the interpretation of the symbols, so of the function symbols and the predicate symbols. And the predicate symbols. So what's an interpretation? It's just the meaning. So for example, you can say that in a model that, okay, so in the previous program, let the set of the objects, I will just do this by an example. So for example, example 1. So let's say the universe is the natural numbers, so it's 0, 1, 2, 3, and so on. And for the interpretation, I will have to define what's the meaning of the even, the odd, the S, and the 0. So those were our 4 symbols, 2 of them being predicate symbols and 2 of them being function symbols. So 0, that's just 0 means 0. Okay, that's an option. And the successor of some natural number n is just, say, n plus 1. Why not? The even n, even is a predicate, so I should tell when is this predicate true. Even n is true and false. True is denoted by 1, false is denoted by 0. So even n is 1 if and only well n is even. It sounds trivial for us because we read the name of the function and we already have some intuition what should it mean, but we will see in the second universe, the second possible model, that it can be something entirely other thing. And let's say odd and holds if and only if the number n is odd. Okay, that can be well structured at this point. And for example, we can say that so the set of so let's the universe be just all the real numbers. Why not? We can say that 0 means, say, 1 as a real number. So this is just an object. Constant function symbols are mapped to specific objects of the universe. It can be 1, it can be 0, it can be square root of 2, whatever. You can define the successor of n as, say, n times 2. I mean, why not? So let's say that even of n is true if and only if, say, n is an integer. Why not? That's also a possible semantics, right? So it's if there is absolutely no built-in predicate, then you are free to interpret this guy as this and as an integer. And you can also say that odd n should denote the same. Odd n is 1 if and only if n is an integer. Why not? Okay. And of course, a model of the logical program P is a set of objects and the interpretation of the predicate symbol such that all the implications are true. Such that all the implications, all the clauses of P hold. Now, an implication is always means universally quantified. So, for example, in our let's just get back to our first example, this guy here. So, in the first universe, the first sentence, the first clause says that if whenever x is an even number, then x plus 1 is an odd number, and it's true. The second actually says that if x is an odd number, then x plus 1 is an even number, and that's also true. And the third one says that 0 is an even number. So it means that the first universe, the first structure is a model of the program. And now let's just check the second. The first statement, and recall that, I will just go back. So in this second example, we had the real numbers. The 0 sign denotes 1, which sounds like crazy, but why not? And s is just multiplication by 2, okay? And both of the predicates mean that the input argument is an integer. Okay, so let's just try to describe what does it mean. So it says that for every real number x, if x is an integer, then x times 2 is also an integer. Okay, that's true. Okay, so if I multiply an integer by 2, that's what sx means, then it will be an integer. Fine. The second statement says the very same. So it says that if x is an integer, then x times 2 is also an integer. Fine. Because both odd and even are interpreted as being an integer. And what does the third say? The third one says that 1, because in this structure, this 0 sign denotes the number 1, the real number 1. So it says that 1 is an integer, and this is also true. So this is also a model of the program. And in a logic programming context, we just describe by these clauses one particular model, and then we just ask questions from the prolog engine, and it will answer our queries by yes or no. But for example, if I just ask the prolog engine whether, say, even of s of 0 holds, then what happens? In the first universe, in the first model of the program, this means that 0 stands for 0, s of 0 is 1, s of 1 is 2, and even means evenness. So in the first universe, the question means that is 2 an even number? And it is. It's an even number. So in the first universe, we can safely say yes. Now in the second one, what does this question mean? 0 is, well, here 0 denotes 1. Okay. S of 1 is 2. S of 1 is S of 2, which is 4, because here we are just multiplying the argument by 2. Okay, so S of 0 is 4 at this point. And the question is whether 4 is an integer. Yes, 4 is an integer. Okay, so far so good. So both queries evaluate to the same thing. But what happens if I just ask whether, say, even of S of 0 holds? Now in the first case, it's asked whether successor of 0, which is 1, is 1 an even number? No, it's not an even number. So in the first model, the prolog engine should say no. In the second model says, okay, so 0 is 1, s of 0 is 2 times 1, which is 2, and the question is whether 2 is an integer. Yes, it is. So you can see that the answer to a specific query is heavily depending on the particular model the prolog engine has in mind. But the question is, which model should we choose? So given a program, and this is the primary question of the logic programming part, given a logic program P, which model should we choose? Should we choose? And that's a very good question. So for example, if you are a machine, then why should you pick this particular model and not that particular model? Who tells you which is the right choice of model? And there is a thing which is called Hairbrand Theory, which says that first a Herbrand model Now we have a logic course for beginners here in SECET, but it's quite possible that you've never heard about the Herbrand model. So Herbrand model, so what a model is? What are the objects? What's the interpretation of the function symbols? And what's the interpretation of the predicate symbols? Now in the Herbrand model, two of these three are fixed. So a Herbrand model is So the objects are the ground terms. So not the numbers, not the weeks of the day, not the natural numbers, not the real numbers, but the ground terms. The objects are the ground terms. And the function symbols are interpreted by themselves. I will get this back. So I get to this in a couple of minutes. The function symbols are interpreted. Well, let's just say naturally. And you are free to choose the interpretation of the predicate symbols. So you are free to choose the interpretation of the predicates. Predicates. Now let's just work this out on an example. So in our first example, we had this something implies or nothing implies evenness of zero, and evenness of x implies the oddness of successor of x, and the oddness of x implies the evenness of s of x. So that was our program once again. And in this context, in this signature, the ground terms are those terms which do not use the variables. So you can use the constants and you can use the function symbols to build up the objects themselves. So in this case, A, the set of objects, is consisting of the zero, because zero is a constant, it's a nullary function symbol. And you can apply the successor function. You can apply the successor function twice if you wish. You can apply the successor function thrice if you wish, and so on. You cannot apply the odd and the even because those are not function symbols, they are predicate symbols, right? So it's a difference. So that's why the ground terms are important, because in a Herbrand model, these the ground terms will be the object themselves. And of course, if you just what's the meaning of the function symbols? Well, if you apply the function fs to the object s of 0, then it should be s of 0. That's just the meaning, right? So it's just a function. It should transform an object onto another object, and this is the way how should you do this. Just simply recolor it to orange if you wish. So if orange denotes the objects and green denotes the function symbols which are not interpreted yet, then a possible interpretation is just color it to the object color if you wish. So it basically says that although you could interpret the s function in some other way, just similarly as we just redefined in the previous example 0 to denote the number 1, this cannot happen here. A function symbol is always denoting a function which is the natural meaning of the function symbol. And these guys have natural meaning because ground terms use the function symbols. Yeah, so you just build up newer and newer ground terms using the function symbols, right? So that's what makes a model a Herbrand model. And a Herbrand extension of a program is defined as follows. You just take the clauses and substitute ground terms in place of the variables in all possible ways. You will end up with an infinite number of ground clauses. So Herbrand expansion, you just substitute ground terms into the variables of the program. So it's a Herbrand extension of the program P, in all possible ways. So I will just use maybe a new slide. No. So for example, for the first clause, there is absolutely no variable in this clause, so the Herbrand expansion of this particular clause will be just itself. So the Herbrand extension of this program above will contain this clause. That's fine. Now for the second one, we have some options, because in place of x I can substitute the 0 and I will get the even 0. If 0 is even, then odd, something is odd, which is odd, the successor of 0. So this x and this x denotes the same. If you are doing one substitution, then you should replace the same x's within the same clause by the very same ground term. If you have an x and a y, then you can just substitute ground terms in place of the x and in place of the y independently. But if your variable is the same, then you have to substitute the same things into it. So, for example, and of course you can substitute s of 0 in place of x in this clause, and you will get, if the successor of 0, I'll just get rid of the parentheses, right? So the successor of 0 is even, then it's odd. What's odd? The s of x. X was s of 0, so it's s of 0. So this is odd, s of 0. And the third is if the s, so I'm just substituting this object here. The successor of 0 object being ground term, because we are in a Herbrand universe. So it's s of 0, which implies the oddness of s of 0, and so on. And by the and so on part, I mean that there is an infinite number of such clauses. And of course, after I got this infinite number of clauses, I still have a third one, which, for example, will contain the odd 0 implying the evenness of s of 0, and so on. So you can just substitute s of 0, s of 0, and so on in place of the x again. So you clearly get an infinite number of clauses by constructing the Herbrand extension. Now, of course, constructing doesn't mean that you have to procedurally generate all of these, because, well, of course, this is an infinite set and you won't be able to finish the generation part itself. But in theory, we have this Herbrand extension, and as I've said, this subject is how a theoretical mathematician views the code of a logic programming language. But there is a very, very good reason to create this Herbrand extension. First of all, there is a theorem that a logic program always has a Herbrand model. So you can just define a Herbrand model, and what should you do? What you should do is just watch these things. I will just erase the upper part of the board right now because I'm trying to make a point here. So we have this Herbrand extension. These are, well, technically these are first order formulae, right? But they have a very, very specific form because they contain absolutely no variables. And without variables, programs are not that hard, not that complex, because even 0, this guy here, well, this is a statement about one particular object, so it's not a variable, not something like that. This is either 1 or 0. This is either true or false. Yeah. And here the even 0 is the very same statement about the very same object, so this should evaluate to the very same truth value. But there is another guy, which is the odd s of 0. Now this guy also should be evaluated to the one single truth value. This is either true or false. S of 0 is one object. In our first example, S of 0 was 1. In our second example, S of 0 was 2 times 0, which is 2. But this is one particular object for which the predicate denoted by odd either holds or not. So this will be also something which is either 1 or 0. And odd of s of 0 is, okay, I can't find the same thing because odd of s of 0 is not here, but it would be here in the second row on this extension. So odd of s of 0 implies the evenness of s of f of 0 would be here somewhere, and in that case this odd of s of 0 should be evaluated to the very same value. And of course, again, there is another guy, say the even of s of 0, even of s of 0. This is a different object, so it's a different predicate regarding the same object as the previous one. So odd s0 is either odd, okay, so that has some value, but it doesn't necessarily have any connection to the even s of 0. So odd of s of 0 is quite independent from even of s of 0. In your head, these might be, well, the complements of each other. A number is either even or odd. But in our second example, you could see that these words could mean the same thing, like it's an integer. Why not? So even of s of 0, this is also a truth value. It's either 1 or 0, and this guy is here, it's the same. But basically, at this point, you only have propositional variables. Variables will take truth values. It's either 0 or 1. So basically, we have a propositional program. So we don't have to care about predicates and functions and objects. We only have Boolean variables, an infinite number of them. Yeah, that's true. But many experts say that an infinite number of Boolean variables is still much better then a finite number of functions, predicates, and objects. Well, you can say that. So basically, that's why we will use this. So we say that after this transformation, the original program looks like the program. The program consists of, so it's just Boolean clauses of the form, and I will just write this in yellow. So clauses of the form P1 and P2 and blah 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 and Pn, implying some Q, with each of these guys being one Boolean variable. So with P1 blah blah Pn and Q being, well, I say that propositional variables, right? It's basically the same as Boolean variables. Propositional variables, say coming from set Z. It's a capital Z, usually denoting the set of propositional variables. So just moving back, in this case I had some propositional variables, say even 0, this was one propositional variable, odd of s of 0 would be another propositional variable, even of s of 0 would be the third, and so on and so on. So for example, now the even odd example can be rewritten to, now let's say that even of the successor of the successor of the successor of the successor of 0 and odd of the successor of the successor of the successor of 0, right? So these are the two types of formulae which we will have. So for example, here you can see that even 0, odd s0, odd even s of 0, odd of s of 0, and so on. So basically these are the only atomic formulae we can create. So let's just denote these guys. So if you have a number n of s's here and can be 0, so let's say, let's call this Pn and let's call this Qn. So basically instead of even 0 I will say P0, and instead of odd of s of 0 I will say just Q of Q2, right? So even or odd, P or Q, and the number of s's is just the n, the index, the subscript of the variable. So so in that case, the z, the set of the variables will be P1, Q1, P2, Q2, and so on. It's an infinite set, and our program will be, so first there was a clause of even of 0. Even means it's P, and 0 means there is no s's, so it's just P0. Okay, this is from the even 0. For the other, so if 0 is an even number, then 1 is an odd number. If, so this is the Herbrand extension coming from one of the clauses. P2 implies Q of 3, and so on. point, 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 dot, dot, dot. And from the second clause, I will get something that Q0 implies P1. Odd 0 implies even S of 0. That's what's written here, but it's more compact in this way. So it's Q of 1, Q1 implies P2, Q2 implies P3, and so on. Okay. And the question is, okay, so this is a program. Which model should we use? So which model? Should we use? Okay, that's a good question. And because of, okay, so let's try to construct. Let's try to derive some facts regarding these clauses. So in a model, all of these implications should be satisfied, which means that if the left-hand side is true, then the right-hand side is true as well. Okay, which means that because of this guy, P0 is definitely 1, because as I've said, the empty conjunction is true. So on the left-hand side we have true. So on the right-hand side we should also have a value of true. So P0 is definitely true. And because of this, P0 implies Q1. Okay, and the left-hand side of this clause is true, which means that the Q of 1 should be 1 as well. Okay, and because of this, and we have this clause there, we already know that Q1 should be true, then P2 is also true. P2 is true. P2 is true. Okay, what do we know? Here, this guy, because of P2 being true, Q3 is also true. Okay, so Q3 is also true, and so on. And at this point, you might just realize that this is the very same structure we had in mind about the natural numbers and actual evenness and oddness. First, just says that 0 should be an even number because P was a shorthand for even. The Q1 means that 1 should be an odd number, 2 should be an even, 3 should be an odd, and so on. We are just generating the very, very same structure which was our first example structure. And, well, if we just set these guys to true and all the others to 0, so let's say all the others 0. So of course P4 will be true, Q5 will be true, and so on. Now if in this particular example we just set all the others to 0, then it's fine, because this implication, for example, will be satisfied because Q0 is a 0, so it's false. And if an implication has a left-hand side evaluating to false, then the implication is true. So if the conjunction, if the left-hand side, if the body of the clause is false, then the clause is true. So it's fine. This guy here is also fine because P1 is 0. This guy here is also fine because Q2 is 0. So all the others are 0 is a model, and this model is actually the same as the one which we used in example 1. Well, of course, the program won't have any intention or anything, any mindset. So the program won't know that we have in mind that the objects are the natural numbers. or the even denotes the actual evenness of a natural number, but by pure coincidence, if you just choose this model, so set those guys to be true, which absolutely necessarily have to be set to true, and set all the others to 0, this model will be the same as the one which the programmer had in mind, well, presumably when the programmer wrote the actual code. So the thing is that this here is an absolutely automatic procedure which creates a model of a logic program, and to create this we did not use any knowledge on the meaning of these words, even or 0s. It was a totally automatic procedure, and by this totally automatic procedure we just ended up to have the very same model of the program which the programmer probably had in mind. And this is good. So basically, to be a good product programmer, you should be really familiar with this actual automatic procedure and write your programs to make sure that this transformation will end up with the very same structure that you have in mind. So, well, to be a good product programmer, you just have to know what what model will the interpreter create for you if you just enter a number of clauses. And if you just enter a few more clauses describing the word you have in mind, at some point you will agree with this artificially created model. Now the thing is, why should we choose this particular model? Set these guys to 1 and set those guys to 1, which should be absolutely necessarily set to 1, and set all the others to 0. It's because the experts in logic programs say that so they call that maybe the golden rule of semantics of logic programs is that the model, so let's say the model we associate to a logic program should be, and I'll just write this in red, should be a minimal one. So a minimal model. A minimal, well, informally this means that I should just assign the lowest possible truth value. 0 is smaller than 1, false is smaller than true. So I should just keep the variables, so I should just keep the values of the variables to be as low as possible. So basically it says that I should really just set those variables to 1 which have to be set to 1. So regarding the question, why did we choose this particular model in the previous example, is answered by, well, this rule of semantics. So it seems that the experts designing logic programs and the experts analyzing logic programs all agree in this particular fact that, okay, so we should have one single canonical model for each program, and a program can have many possible models in this propositional model, so after the Herbrand transformation. And amongst these possible models, we should just pick one which minimizes the truth values of each variable used. Now we will be more precise on that. So we will be more precise in the next video. But right now I'll just finish this video, and in the next one we will create some math about this minimization and orderings and partial orders, which we'll use till the end of the course. Well, till then, bye bye.